Alrighty, hello AP Chemistry. We're going to talk about nuclear chemistry now. You're going to be familiar with most of this knowledge, this initial knowledge I'm getting ready to tell you a little bit more about. You've heard of alpha particles, you've heard of beta particles, you've heard of gamma rays. Those are the types of decay processes that we're going to talk about, plus one more called dealing with positrons. And some of the history will be somewhat familiar to you as well. You'll recognize some of the scientists. So this first video is meant to be some review and some details that you're not aware of yet. But thus far, we've only really talked about changes that occur with electrons in atoms. We have not talked about the changes that occur in the nucleus, because most of the time, chemical reactions don't even involve the nucleus at all. So we're going to dig into the details of how neutrons can be changed and how proton numbers can be changed, thus changing the atom. So let's go ahead and start with the history. The first man here, Dalton, should be familiar to you. So he's actually the one who developed the atomic theory. He talked about atoms being indestructible. However, we do know that we can get protons, electrons, and neutrons out of an atom. So that was false. Also, his statement about the isotopes, and we know that there are isotopes of atoms as well. In 1869, Mendeleev and his periodic table were established, and so he organized the PTOE based on atomic masses. Now we've got it based on atomic number, but we know that they correlate due to the fact that protons and atomic number also have mass. Last, you've got J.J. Thomson. You know him from the mustache. He developed the plum pudding model, which we now know to be false. He developed that in 1896, and so his version of the atom was not exactly true as to what we found out today. So slowly building up, we've discovered new things about the atom and about the nucleus of the atom. In 1896, Becquerel, he actually started using uranium salts in some experiments. His experiments were really actually pretty cool. So he took rocks with uranium in them, because we have a lot of rocks in ores with uranium salts in them. He set them outside, and he set them outside out in the sun all day long. And then he took them back into a darkened room in his labs for observations. He put the rocks into a drawer with some photographic plates, and he tried to see what would happen from the energy from the sun being kind of absorbed into the rocks and how that would affect the photographic plates. So what he thought was actually occurring was he thought that the sun was being absorbed into the rocks, and the rocks are storing that energy, and then later releasing this energy on the plates, which would resulted in exposure. So just like any old photograph is exposed, it changes the white and the dark. We learned a little bit about that with redox. So, however, he also took these rocks out on cloudy days where there was no sun or out in the dark, or he didn't take them outside at all. And he did the same experiment. He put them in drawers with photographic plates, and he found that they still exposed the photographic plates. Therefore, it was not the sun energy that was being absorbed and then released. It was actually the uranium in the rocks that was giving off its own types of rays. So because it was uranium and because it was coming from the rocks, he called these the name of this phenomenon uranium rays. We now know this as radioactivity, but this was not the fact in 1896. However, 2 years later, Marie Curie and her husband Pierre Curie found the same thing with different types of elements. And they said, I don't think it's just uranium, because we need to come up with a more universal name for this thing that's more inclusive of all the elements that can actually perform this phenomena. So they called it radioactivity. So knowing now the phenomena is called radioactivity is one important thing. So it's not just uranium, there's other elements that can do this. Radioactivity is any spontaneous release of energy by an object. All right, moving further, we've got to actually discover the alpha particles and beta particles soon after Marie Curie and Pierre did their research. And so we've discovered these, we've named them alpha radiation and beta radiation. We know a little bit more about the alpha particle, meaning that it's actually going to be a helium nucleus. And if you remember, Rutherford's gold foil experiment, you'll remember that he shot alpha particles at the gold foil. He noticed these odd deflection patterns, which led to the fact and the observation of a dense nucleus, and so therefore he discovered the nucleus. Later in 1913, Henry Moseley came up with the idea of atomic number, and therefore he figured out that we should arrange our periodic table according to the atomic number, which is also representative of the proton number. And so his important discovery or establishment was the current periodic table arranged by atomic number, not Mendeleev's, which was composed of mass numbers. All right, so let's actually talk about these particles now. So you remember these, you probably remember some of the symbols, so let's go ahead and start using the symbols and actually how we can stop these particles or rays from penetrating certain objects. How can we block them? So here's what an alpha particle looks like. It is actually a helium nucleus. And so you'll notice the top number 4 is representing the mass, which the mass is consisting of 2 protons and 2 neutrons. This is the mass number. Then you've got the atomic number, which is just the number of protons. So this is fairly large for a radioactive particle, and we label it kind of like a fish. That's the Greek letter alpha, and it's not just the entire atom though. It is only the nucleus, and so it's consisting of just the protons and just the neutrons with a total mass of 4. And so don't forget that the mass number is always equal to protons plus neutrons. This is a fairly large radioactive particle. We're going to talk about the penetrating ability now. So because these are big and they're slow, you don't need much to block them. They're going to be just hindered by a couple of sheets of paper. Our skin actually naturally stops these alpha particles from penetrating our body as well. So they're no danger to us in terms of radiation or radiation poisoning. So 1 or 2 sheets of paper should work. All right, so moving down to a little bit more of hazardous particles called beta particles. And they are pretty much exactly the same thing as an electron. They have no mass because electrons have negligible mass. So their symbol here is just an electron with the mass indicated and the charge actually indicated as well. And we're going to talk about how we're going to use this negative and this symbol of the 0 on top, E representing the fact that it's the same as an electron, and the negative number, which we will represent as a charge. So it's got a charge of less than 0 with no protons, so we have to indicate that as a -1 to show that it would actually decrease the atomic number if we were trying to include this in atomic number. But it has no mass. So because this is really, really small, it's just the size of an electron, which is extremely tiny. They're very, very fast. So they're a little bit harder to stop, but a thicker object should do. So something like aluminum foil or a thin sheet of wood will stop this. So it's thicker than paper and it's more durable than paper. Okay, so now we're going to get to the big boys. We've got gamma rays. Now, gamma rays are actually not particles at all. They're just energy. So think of the electromagnetic spectrum. You can Google one and find a picture of one. You'll find that gamma rays are actually wavelengths. So since it's not a particle, there's no mass. And this is how we draw this. Kind of like an upside down fish, but it's actually, it looks more like a Y if you actually draw the Greek letter. And so since there's no mass, we have a 0 as the mass number, and since there's no charge to it either because it's not a particle, we put a 0 down there as well. And so this is actually this is more dangerous. It's very close to X-rays on the electromagnetic spectrum. So they're super fast and they can penetrate well because they're just energy. So this is going to require much more protection from penetration. Something like concrete or a couple of centimeters of lead. So several centimeters of lead should ring a bell with you. So when you go to the dentist and you get an x-ray, they put a lead vest on your chest if they're just x-raying your teeth. Or if you go get an x-ray at the doctor, they'll put a lead vest on you on your whatever body parts are not being x-rayed because they just want to expose you to the radiation in that particular location and not give you an overdose of this radiation, because these are particles that can penetrate you and cause mutations to your DNA, if you remember that from biology. So you want to get the lowest level of radiation as possible in terms of gamma or x-rays, which is why you only get, like, your dentist only x-rays your teeth once a year or so. All right, so now we're going to get to the positron. So this is the really interesting one because you've never probably heard of this before. So this is a type of antimatter. It's called an anti-electron. And it's different than an electron because it's anti-electrons. So antimatter is actually opposite in nature of normal, ordinary matter. So what scientists have found, when they've been studying the universe, they found that there wasn't enough stuff to account for all the observable events in the universe. So they came up with the idea that there are opposing particles for all the particles of matter that we currently know about. So for every proton, there's an opposing piece of matter. For every electron, there's an opposing piece of matter, which we call the positron. And then for every neutron as well, there's an opposing particle of matter. And these aid in balancing the forces of the universe. We can get into this a lot more. This is a really interesting field, very cool. You know, it can lead to astrophysics and stuff like that. We can learn about the universe. So with this opposing nature, it's going to have opposite magnetic spin, which we're going to talk about with quantum mechanics, as well as an opposite symbol or opposite charge. So this is how we draw this one. It's still an electron for the most part, so it's got zero mass, which has, you know, no protons, no neutrons. However, it's got a 1+ charge. But this 1+ charge is not caused by a proton. It's just the charge of the positron. So no proton, and the reason there's no proton is because there's no mass. So you have to know that +1 is referring to the charge of this quote-unquote electron here. Its penetrating ability is also something that's kind of unknown. We don't know as much about antimatter. We just know that when normal matter and antimatter come together, they annihilate each other and there's a large burst of energy. We just don't understand the penetrating ability of positrons, but I can imagine they're quite the same as an electron. So, but we'll move on from that point. So it's useful to know about some of these new discoveries of antimatter. Like, you know, they can actually start to use these in PET scans. They can use them in ion therapy. They can use them for generating better energy from fuels. They can use antimatter in weaponry. So we're going to start to talk about these a little bit more. It's a very cool field. And if you want to know more, here you go. So if you want a quick break from me, there's a couple of 2 videos right here. You've got antimatter and thunderstorms. It's quick and easy and it's kind of cool. And then there's a couple of things from the BBC, which you'll find interesting if you like the field of physics and antimatter. And you'll see here, this is what an alpha particle looks like. There's 4 things there, 2 of which are protons, 2 of which are electrons. Protons and neutrons, which is resembling a helium nucleus, not the entire helium atom. And then I've got this whole other picture here to resemble everything we've talked about: beta particles, alpha particles, and then we're going to start to talk about gamma rays a little bit more and electromagnetic forces. All right, so last thing on this video is mainly about decay equations. So let's go ahead and talk about how beta and alpha decay can occur. Whenever we talk about alpha decay, since you're getting rid of an alpha particle, one of the products is going to be an alpha particle, which is a helium nucleus. So whenever it decays, you're going to represent that in the product side of the reaction because you're getting rid of that. So with this example here, we're going to start with just the information of being given that this is undergoing alpha decay. So the first thought in your head is that I need to get rid of an alpha particle. The second thought is kind of like the conservation of mass or matter. So whatever you have on the reactant side in terms of mass and mass number or atomic number, it's going to be equivalent to what's on the product side in terms of mass and atomic number. So we're going to decay this single reactant into a helium nucleus and something else. That something else is going to balance and equal what's on the reactant side of this equation. So this is what we kind of start to look like. Currently, we just have the helium nucleostron, but since the overall mass on the reactant side is 222, you know that the product side is also going to equal 222. So that means 4 plus something is going to give you 222. In this case, it's 218. That means 218 plus 4 is equal to 222. Secondly, you've got an 88 atomic number on the reactant side, and you've got 2 and an unknown number on the product side. So 2 plus blank is equal to 88. That's 86. So in this case, our atomic numbers also add up. 2 plus 86 is equal to 88. So now we just need to figure out what atom this is representing, or what element. So you look on your periodic table and you'll find that 86 is radium. Excuse me, is radon. Radium is 222 and it's undergoing alpha decay, which it's spontaneous releasing an alpha particle and it's turning to radon. All I did was look at atomic number 86 and found that one on the periodic table. So, rules. You need to make sure you know what is being expelled if it's alpha decay. 2, you need to do the summations. You need to do the math on each side and then figure out what atomic number 86 or whatever it may be is representing from the periodic table. Second, we've got beta decay. So if it's beta decay, you have to know what's being produced. Beta particles are pretty much just an electron, but you've got that -1 down there. So one of the products is going to be that electron. So this is a little bit different. This is a little bit unusual. So you've got this neutron in the nucleus, and the neutron actually, when it undergoes beta decay, it turns into a proton and an electron, and that electron gets ejected as a beta particle. The proton stays in the nucleus. So this is what happens. So overall, we're going to see slight differences in the atomic number, but we won't see much in the mass department there. And the reason that this actually occurs, we're going to talk a little bit more in the second video, but this needs to occur because we want to make sure our atoms are stable. And the way they're stable is if they have the appropriate number or a stable number of protons to neutrons ratio. It's called the neutron to proton ratio. And so if they're not in that little designated ratio, then they eject certain things to get down or up to that ratio. We're going to talk about that a lot more. Okay, so but what's weird about this is the electron came out of the nucleus, okay? Because your neutron turned into a proton electron. This makes sense in the fact that neutrons are neutral, so they have part positive and part negative charges, which means it's kind of partially a proton and partially an electron. So just make sense of it as you can. But the weird part is nuclear chemistry, so we're talking about electrons coming out of the nucleus, which is the unusual part. Okay, so we've got carbon-14 down here. Carbon-14 has atomic number 6. Whenever an electron is ejected, this is what it looks like. We have to fill in the blank. We're using the same rules as before. The mass numbers have to equal reactants and products, and the atomic numbers have to equal reactants and products. So 14 plus 0, or excuse me, 14 minus 0 is just 14. Therefore, we still have 14 on the mass side. And then we've got 6 is equal to negative 1 plus x. We don't know what this x is. So do not forget about your little negative. You're going to have to double check your math twice here. So this is actually going to be a 7, meaning 7 minus 1 is equal to 6. Don't forget that. It's easy to mess up. So if that's atomic number 7, when you look on your periodic table and you look at atomic number 7, that's going to be nitrogen. And there you go. That's how you do the beta decay equation. Second, we've got a couple different ones. These are some that you've probably never heard of. So these are called electron capture and positron decay. So electron capture is slightly different. It's where the particle is actually a reactant. So we've got this particle, this electron, which is the same symbol as before. But it's actually going to be part of the reactant side, not the product side. So here we've got vanadium 50, and this is a kind of opposite of beta decay. You've got a proton and an electron coming together to become a neutron. So now this electron is becoming incorporated into the nucleus, and it does so by combining with a proton in order to make a neutron. So make sure you know it's opposite of beta decay. So it's like electrons are bombarding the nucleus. And this is mainly only going to occur in synthetic nuclei. These are not natural nuclei. These are man-made elements. And think about the ones at the bottom of the periodic table, like californium, einsteinium. Those are ones with, more human names, I guess you could say, that are synthetically made. Okay, so we've got vanadium 50, and then we're going to add an electron to that on the reactant side. So using your same rules, you want the top numbers to equal, and you want the bottom numbers to equal on reactants and product sides. So vanadium 50, so 50 plus 0 is 50. And then you've got 23 minus 1, which is 22. Whenever you look up that atomic number on the periodic table, you'll see that it's titanium. Okay, so that's how you write the decay equation for electron capture. And make sure you know that electron is a reactant. Okay, one more, positrons. Positron decay is actually also only with synthetic nuclei, and we're decaying one positron. So what's the positron symbol? 0 plus 1e. And this is actually a product because it's being decayed, it's not being captured. And this one is has a lot more to do with the properties of antimatter. So we've got a proton that magically turns into a neutron, and it's not magic. There's no alchemy involved here. But you've got, normally you would also have an electron being involved, like in beta decay. But this is actually a proton that's translating itself into a neutron with the help of neutrinos and which are weakly interacting elementary subatomic particles. Has a little something to do with quarks too. We can get into the big antimatter discussion later. But positrons will actually be a product here. So let's go ahead and write it as a product. We've got cobalt 54, and it's going to be decaying by expelling a positron. Same rule, you want to summate both the atomic number and the mass number. So 54 is equal to 0 plus 54. And then you've got 27 on the bottom is equal to 1 plus blank, or x. So that number is actually going to be 26. And then you look up atomic number 26, and you'll see that it's iron. Alright, and so the only weird thing about this one is this little proton turning it into a neutron. You don't have to understand why, but it's because it's mainly going to be dealing with antimatter. Okay, so we're pretty much done with this section. Just make sure that you do your problem set and you do some questions involving this. Make sure you took your notes appropriately. The second part that we'll be talking about is about predicting stability of nuclei, talking about that ratio of protons and neutrons, how you would predict these decay processes, and also fission and fusion reactions. So good luck with this. See you in the next video.